Deep within the jungles of the Yucatan Peninsula, a silent history is written in stone. It tells a story not of kings and conquests, but of sun and rain, or, more precisely, the catastrophic lack of it. For centuries, the collapse of the magnificent classic Maya civilization has been one of archaeology's greatest mysteries. How could a society famous for its sophisticated writing, complex calendars, and towering pyramids just vanish, abandoning its great stone cities to the jungle? While theories have ranged from warfare to disease, a detailed and compelling story is emerging from the dripping water inside ancient caves. Down in these dark chambers, stalagmites have been growing drip by drip for millennia, creating a near-perfect archive of climate history, one that speaks of the profound droughts that brought the Maya to their knees. This is the world of astro-climatology, a field that reveals how cycles in the heavens can drive climatic shifts on Earth, shifts that can forge or fracture human destiny. By deciphering this record in stone, scientists are not just solving a historical puzzle, they are uncovering a powerful cautionary tale about what happens when the climate that sustains a civilization changes. Between roughly 250 and 900 AD, the Classic period saw the Maya civilization reach its absolute peak. Across modern-day Mexico, Belize, Guatemala, and Honduras, a network of powerful city-states like Tikal, Copan, and Calakmul thrived. Their people were master astronomers and mathematicians who independently conceived of the number zero. They were architects of sprawling palaces and pyramids that touched the sky. And they developed a complex hieroglyphic script, the only fully developed writing system in the pre-Columbian Americas, which they used to record their history on stone monuments called stelae. Then, in the period known as the Terminal Classic, from about 800 to 1000 AD, everything changed. In the southern lowlands, the heartland of the civilization, the carving of monuments stopped. The construction of grand buildings ceased. One by one, the great cities were abandoned. Within a few generations, huge areas of the central Maya region were almost completely depopulated. This wasn't a single event, like a massive earthquake or a sudden plague. It was a slow decline over more than a century, which makes singular catastrophes unlikely culprits. Now, it's crucial to understand this collapse was not the end of the Maya people. Millions of Maya live in the region today, carrying on their rich cultural heritage. Instead, it was the disintegration of their political and social system in that southern heartland. Power and people shifted north, to the Yucatan Peninsula, where cities like Chichen Itza and Uxmal rose to prominence for a time. The reasons for the southern decline have been fiercely debated. Evidence points to a complex web of problems: increased warfare between city-states, environmental damage from overpopulation and intensive farming, and disruptions to vital trade routes. It was a society under immense stress, yet woven through all these theories is a persistent and powerful thread: climate change. And the most detailed, high-resolution evidence for this climate change comes from the darkness of caves. So how exactly does a cave act as a weather station? The key lies in stalagmites, those familiar cone-like mounds that grow upwards from a cave floor. The process begins with a single raindrop. As rain falls, it absorbs carbon dioxide from the atmosphere and the soil, becoming a weak carbonic acid. This slightly acidic water then seeps through the earth, dissolving limestone, which is mostly calcium carbonate, along the way. When this mineral-rich water finally reaches a cave ceiling and drips, it hits the air inside the cave and releases its dissolved carbon dioxide. This simple chemical change makes the water less acidic, causing it to precipitate its mineral load, leaving behind a microscopic ring of calcite. Drip after drip over thousands of years, these tiny calcite layers build upon one another to form a stalagmite. Just like the rings of a tree, these layers create a physical timeline of the environment directly above the cave. Because the water that forms them is a direct product of local rainfall, These layers trap chemical information about the climate conditions for the exact time they were formed. Scientists unlock this ancient weather data by analyzing isotopes of oxygen trapped within the calcite. Oxygen comes in two main stable forms, a common, lighter version, OXYGEN-16, and a rarer, heavier one, OXYGEN-18. The ratio of these two isotopes in rainfall is highly sensitive to climate. During periods of drought, for instance, evaporation is higher. The lighter OXYGEN-16 evaporates more easily, so the remaining water in lakes and rivers becomes enriched with the heavier oxygen-18. When this O18 heavy water seeps into a cave and forms a stalagmite layer, that layer gets a higher concentration of oxygen-18. By drilling a core down the central axis of a stalagmite and analyzing tiny samples from each growth layer, scientists can measure this oxygen isotope ratio and reconstruct a remarkably detailed history of rainfall and drought. Using precise uranium-thorium dating techniques, they can then assign highly accurate dates to these layers, sometimes with a resolution that can distinguish between individual wet and dry seasons over thousands of years. This method gives us a timeline of past climate far longer and more stable than tree rings. And when scientists applied this technique to the caves of the Yucatan Peninsula, the results were stunning. Groundbreaking research from caves like Grutas Tzobna in Mexico has provided a high-resolution climate record for the exact period of the Maya collapse. One particular stalagmite allowed scientists to reconstruct rainfall patterns for every single wet and dry season between the years 871 and 1021 AD. The data was stark. It revealed that the Maya suffered through multiple, prolonged droughts that were far more severe than anyone had previously imagined. The study identified 8 separate wet season droughts that lasted for at least 3 years each, but most catastrophically, it pinpointed one devastating drought that persisted for 13 consecutive years, from roughly 929 to 942 AD. The Maya were skilled water managers. They built complex systems of reservoirs, canals, and underground cisterns called choltuns to cope with the region's naturally seasonal rainfall. Their entire society was structured around surviving the annual dry season. But the droughts recorded in these stalagmites were on another scale entirely. A multi-year failure of the crucial summer wet season, upon which their entire maize-based agriculture depended, would have been calamitous. A drought lasting over a decade would have been an apocalypse. Such extended dry periods would have completely exhausted their water stores, leading to crop failures, famine, and widespread thirst. The timing of these climate events aligns almost perfectly with the archaeological evidence. During the periods of the most severe drought identified in the stalagmite record, the historical record carved in stone by the Maya themselves goes silent. In major centers like Uxmal and even the powerful northern city of Chichen Itza, the construction of monuments and the inscription of dates on stelae abruptly stopped. These inscriptions were the hallmarks of a confident and functioning elite class. They were public declarations of a ruler's power and legitimacy, which was deeply intertwined with their claimed ability to mediate with the gods, to ensure agricultural prosperity and bring the rains. With the rains failing year after year, decade after decade, their power would have crumbled along with the crops. The people would lose faith in leaders who could no longer deliver on their most fundamental promise. Further research from other caves corroborates this link. A 400-year climate history from Uxtlahuaca Cave in southern Mexico showed that an unusually wet period coincided with the rise of the great city of Teotihuacan, a major power in Mesoamerica. This was followed by a 500-year drying trend and a severe drought that corresponded exactly with its rapid decline around 550 AD. The pattern is consistent. Wet periods foster growth and prosperity, while prolonged droughts trigger social and political collapse. So while the stalagmites provide the what and the when of the droughts, the next logical question is why? Why did these catastrophic droughts happen? This is where we get to the astro and astro-climatology. The cyclical nature of the droughts suggests they weren't random events. They were likely driven by larger, predictable patterns in the climate system, patterns influenced by astronomical cycles. One of the primary suspects is variation in solar activity. The sun goes through natural cycles of higher and lower energy output, like the famous 11-year sunspot cycle, but also much longer-term fluctuations. These changes can influence Earth's climate. Periods of lower solar activity can cause shifts in atmospheric circulation. Specifically, it can cause the intertropical convergence zone, a crucial belt of rainfall that encircles the globe, to migrate southward. For the Yucatan Peninsula, which sits on the northern edge of this rain belt's summer position, a southward shift is devastating. It means the life-giving summer rains are drastically reduced, leading to severe drought. Another potential driver relates to Earth's own orbital mechanics, known as Milankovitch cycles. These are long-term, predictable changes in Earth's orbit, its tilt, and its wobble. While these cycles operate on timescales of tens of thousands of years, they are the fundamental pacemakers of Earth's ice ages and major climate shifts. The droughts that struck the Maya happened during a period of high solar radiation in the northern hemisphere summer, which paradoxically may have created atmospheric conditions that favored more intense, recurring droughts in that specific region. And finally, you have the intricate dance of ocean-atmosphere systems, like the El Niño Southern Oscillation or ENSO. We know that strong El Niño events are linked to drier conditions in Mesoamerica. The frequency and intensity of these events can themselves be influenced by those longer-term solar and astronomical cycles. The picture that emerges is not one of a single cause, but of a complex, interconnected system. Subtle changes in the sun's output or Earth's orbit can trigger a cascade of effects, altering atmospheric and oceanic circulation and leading to persistent, civilization-altering droughts on a regional scale. The story written in the Stalagmites of Yucatan is a powerful and sobering one. It reveals with chilling clarity how a civilization, even one as advanced and resilient as the Maya, was ultimately vulnerable to the rhythms of the climate system. The collapse was not a singular event, but a complex process driven by many stressors: war, politics, environmental degradation. Yet the relentless, multi-decade droughts appear to have been the decisive blow that shattered the foundations of their society in the southern lowlands. The failure of the rains led to the failure of crops, which led to famine, social unrest, political turmoil, and ultimately, the abandonment of the great cities that had stood for centuries. The silent, stony archives of the Earth's caves have given voice to a history that was otherwise lost. They stand as a testament to the profound link between the cosmos, the climate, and human civilization. And as our own society grapples with an unprecedented rate of human-caused climate change, the whispers from the stone offer a timeless and urgent warning. The resilience of any civilization is ultimately dependent on the stability of the environment that sustains it. The Maya did not and could not see the droughts coming. We can, and the record of their fate, etched in the heart of the earth, implores us to listen and to act.